Okay, so this is chapter 13, the title Temperature Kinematic Theory. But as you will see, we won't really see too many new topics. No, it's not really new material. One of the main topics of this chapter is PV equals nRT that you're very well familiar with. Well, let's start with the discussion. So nowadays we take for granted the matter is made out of atoms. But there were many discussions up to the point where people arrived at a consensus about that. The idea comes, at least goes as far as the Greeks, no, but as a philosophical point, the idea that the atom was something that could not be divided. Nowadays we know that this word is not even so appropriate, no, because it can be divided. We have in the atom the nucleus with neutrons and protons and the electrons around. But this whole discussion that goes up to the Greeks is just philosophical. Now, where are the experiments that finally convince people that matter is really made of atoms? One of the most famous experiments is the Brownian motion. So this drawing here is trying to depict the idea of the Brownian motion. Let me show to you a short movie about that. But let me explain first. So the idea is Brown was a botanist, no, not a physicist or a chemist or anything like that. He was a botanist studying plants, and he did some experiments where he put pollen in a recipient with a fluid, and he saw these grains of pollen moving around. So this is a short video that can give you an idea of what he saw. So you see those little grains jittering a little bit, and the question is, how can we explain that? Well, nowadays that we know that matter is made out of atoms, that in that recipient with that liquid was made of some molecules, we understand what is behind the Brownian motion. And those little grains, those tiny particles, were being bombarded by those molecules, even though we cannot see them. They are there moving and colliding against those grains, and that's what we get to the little jittering motion. So that was a good first direction, a good first experiment, or one of the first experiments trying to convince us that matter was really made of atoms. But let me tell you, Brown, at that point, when he saw that, his first idea was that that motion was probably related with life, because he was playing with grains of pollen. But then he started doing this experiment with other inorganic particles, and he saw the same thing and said, "Oh, that has nothing to do with life." And it's a beautiful paper, many pages of different experiments for him to conclude that. And it was Einstein who did the theory for the experiment in 1905. 1905 is the miraculous year for Einstein. That's the year where he published 4 outstanding papers. One was this one about the Brownian motion, one was about the photoelectric effect, and 2 about relativity. And then with this theory, Einstein was able to show, measure, and calculate the size and the mass of these atoms. Just as curiosity for you, as I said, it was very polemic to finally convince the scientists that matter was really made out of tiny entities. And one of the famous scientists involved in this sort of research was Boltzmann. So let me just show to you a picture of Boltzmann. Here you have Boltzmann. And he's one of the fathers of statistical mechanics, and he developed his whole theory of statistical mechanics based on the atomic theory. And he had enormous resistance. Now, so much so that he ended up committing suicide. Well, people say that he committed suicide because his theory is not so well accepted. Well, probably he was very much depressed also. And since I'm mentioning Boltzmann, I would like to tell you about this other person here who is very special, Lisa Meitner. Lisa Meitner was Boltzmann's student, and she was one of the first women to go to a university, the University of Vienna, one of the first women to become a university professor. She was an incredible physicist. And if you have the time, I really recommend this video, at least to get a little idea about Lisa Meitner. She was a Jewish woman, extremely intelligent, and she was persecuted in the war and so on. And she was the research that she developed eventually led to the development of the atomic bomb. Very well, so let's come back to our chapter. And well, so there we are. Now a lot of discussion to arrive at the idea of atoms. In this slide there is one more thing, and which is just this sentence that you see here, the atomic mass or molecular mass. So what we are talking about here is just, this may show up later in some of the problems, but what is it that we call an atomic mass unit, this 1U? Well, this is approximately the mass of a proton or a neutron. They have similar masses, and the value is given here. How do we arrive at this point? We say that it's with respect to the carbon-12. Now the carbon-12 has 6 protons, 6 neutrons, and we associate with the carbon-12 12 units. So you see that this, therefore, 1 unit is more or less the mass of 1 proton. And so this is something that may show up later. It's a bit out of place in this slide, but I'm just following your book. Okay, next slide, you see the phases of matter. We already mentioned that, and of course you know these 3 phases very well. We mentioned this phase of matter when we are talking about fluids. We also mentioned there that besides solid, liquid, and gas, there are other phases of matter like plasma. But here they show up again because now, instead of thinking about these different phases of matter from a macroscopic point of view, we are changing our perspective and seeing it from a microscopic point of view. So what determines that something is a solid or a liquid or a gas from a microscopic point of view? Well, a solid is this kind of substance where the atoms are very much connected, closely connected, strong forces, so they're not moving much. So that's what you see in this part, figure A, where we have like a lattice. In the liquid, they are not so much attached, so the forces are not so strong among these molecules. And in the gas is the weakest force. They are moving very fast and very far from each other, so they can fill the whole container. All right, let's continue. Next slide. Next slide is introducing finally the concept of temperature, which is the title of this chapter, temperature and thermometer. So what is temperature? Well, it's a measure of the sensation of how hot or how cold. What does it mean to have something that is very hot? Well, again, from this atomic perspective, from the atomic theory of matter, what we know is that water that is very hot, what does it mean? Those molecules are moving like crazy, colliding very fast. Now, once I put my hand there, they collide against my hand very hard, very fast, and that's what means to be hot. So hot is associated with kinetic energy, with the speed of these atoms or molecules, and we'll talk more about this later. Now, at this point, we are just going to talk about what happens to the properties of matter as we change the temperature. And what we'll have in mind now is the idea of expansion. We know that most objects expand when they get hot. Not all. There are some exceptions. Water is an exception, and we will see more about that at certain temperatures. But in general, most materials just expand when they are heated up. Some consequences of that, well, you see in this drawing for this road, you must have notes when you get to a bridge, there is always a bump. There is, and why? Because what links the bridge with the rest of the road, usually there is some spacing, as you see here. And why is this spacing there? Because the road may expand, the bridge may expand more than the road. Now, the road is attached to the ground and so on. The bridge is hanging up there, so it may expand more or contract more. And So this little hole in between the road and the bridge is to take into account these expansions and contractions. Other consequences of expansion due to temperature. Well, we can use that to measure the temperature. The fact that things expand can be used. The fact that things expand is used in the idea of the thermometer. Here we have an example of a thermometer. And what do we have here? Inside this glass, we have some liquid, and this liquid expands more than the glass as the temperature increases, and then we can put some scale here to measure this change in temperature. Another idea for a thermometer is this one that you see on the right. What we have here is two different metals. The green and the blue are indicating two different metals. Once they heat it up, one of these metals may expand more, in this case the green, and the thing bends. It bends. If it was attached with a coil, then the coil would stretch, and I put this associated with a scale, and I also get there a way to measure temperature. Okay? All right, so this is just the theory behind, some discussion behind, but now let's start really trying to solve some few problems. How do we measure temperature? Now we need to associate with that some scale. And there are different scales available out there. One is Celsius, which is the most common one. Now most countries in the world use Celsius. The other one is Fahrenheit, which is a bit surprising that some countries still use Fahrenheit. Just to give you an idea, I searched for what are the countries that still use Fahrenheit, and you see very few: Bahamas, Belize, Cayman Islands, Palau, and the United States. So it's a very, very few countries, and most of them tiny countries except for the United States. So here you can see the map, Alaska, and the US, and then you can hardly see the other countries. They are around here, tiny islands, Belize and Palau out there. Very well. The other scale is Kelvin, which is very much used in science, and it's related to Celsius. Okay, now since we have these different scales, how do we go from one to the other? So what you see here is an idea on how can we change from Celsius to Fahrenheit, especially for those who are Americans. Well, if you travel around, how can you know, how can you transform from one temperature to the other, and vice versa. For the non-Americans who come to the US, how can they make this conversion? So let's see. The idea is very simple, and what we have here is, I'm going to mark the two temperatures, the two main temperatures that are behind the scale for Celsius, which is 0. Let me put my pen here. So 0. 0 is the temperature, 0 Celsius is the temperature where the water freezes, and 100, which is the temperature for the water to boil. And suppose I'm going to try to find out this temperature here in between. Either I want to find this temperature here in between Celsius, or I'm going to be given this temperature in Celsius and I want to find it in Fahrenheit. Okay, now the other scale in Fahrenheit, I'm going to put the numbers associated with all these three temperatures in Celsius that I have. So 0 Celsius, which is the temperature for water to freeze, is in Fahrenheit 32 Fahrenheit. 100 to boil in Fahrenheit is 212. And this temperature in between, I'm going to call it TF. Okay, so how can I go from one to the other? What we do is play with the ratios. So I go TC minus 0, okay, so TC minus 0 divided by 100 minus 0. Okay, so I'm going to play with these ratios. This ratio is equal to the same ratio in Fahrenheit, which means TF minus 32 divided by 212 minus 32. So this is what you need to convert from one to the other. Now, if you are given the temperature in Celsius, you can find it in Fahrenheit and vice versa. You can try to simplify this equation a little bit. So we can write this as Tc over 100 equals to Tf minus 32 divided by 180. Can also go a little further and write this 100 divided by 180, which gives us 5 divided by 9, Tf minus 32. Okay, so this is the way to move from one to the other. So let's see the first problem here. Well, they are telling us that the normal body temperature is 98.6 Fahrenheit, so they're giving us the temperature in Fahrenheit, and they want to know what is this in the Celsius scale. Okay, so you can stop the video now and try to solve this problem. But the idea is very simple here, right? We want to find the temperature in Tc, and we have everything else. 5 divided by 9. Instead of the Tf, I'm going to put 98.6 minus 32. Solve this problem, and you're going to get 37 degrees Celsius. Okay, so let's stop the video here, and we are going to continue soon.